The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to Lab Manager's Tech Trends webinar series. I'm Tanuja Kopal, contributing editor for Lab Manager, and I will be moderating today's webinar, which is focused on new chemistries and improvements in columns now available for liquid chromatography. We have with us today a panel of 4 experts representing some of the leading vendors in the field. And we will be getting their perspectives on the recent trends in the LC columns market, and we'll also be getting their advice on how you should go about picking the column that best suits your analyte, your separation, and also your instrument needs. As always, we will keep discussions very informal and very interactive, and you will be able to ask questions and get answers in real time from our panelists. So please feel free to send along any comments or questions anytime during the webinar by typing it into the question box that appears on the right-hand side of your screen. We will begin addressing your questions right after our 4 speakers have given their talks. Today's webinar will also be available for viewing on Lab Manager's website for 6 months. The website also hosts a number of other resources like technical bulletins, application notes, white papers, and some of them are specifically related to HPLC and UHPLC, which you may find useful. In our closing slide, we will also provide you the email addresses of all our speakers, so you can reach out to them for a copy of their slides, because you will not be able to download a copy of their slides off of our website, so you will have to reach out to them directly. And I'm sure they'll also be able to provide any further guidance on this topic. So with that, let me now turn it over to our first speaker, Dr. William Long, who is an application scientist at Agilent Technologies. Bill joined Agilent in 2001, where he currently works in the LC columns marketing group. His work includes automated method development using small particle columns for pharmaceutical and chemical analysis, and applications development using the poroshell columns for food and pharmaceutical analysis. Welcome, Bill.
Thank you. Oops. Sorry, I'm trying to. Now it's not working. There we go. Today I'm going to talk about selectivity in reverse phase LC using superficially porous columns. Now, what options do you have for high-speed analysis and high resolution? Well, you have several different ones. You can use the UHPLC, or ultra-high performance liquid chromatography, or HPLC with the more traditional 400 bar chromatography limits. You have a whole different arrangement of different types of columns. Particle sizes typically 5, 3.5, 2, 2.5, or sub 2 microns. Now, in order to get high resolution analysis, one approach is to select columns with smaller particles to maintain resolution with a shorter column. The benefit of this approach is that the separations can be matched on different particle sizes for flexibility in different labs or across an organization. Now, what I'm going to do today is introduce some of our new column phases with superficially porous columns. Now, we introduced these a while ago, and the typical poroshell 120 columns have about 90% of the efficiency of sub 2 micron columns with 40 to 50% lower pressure, over two times the efficiency of a 3.5 micron particle. And what makes it really very useful is a 2 micron frit, which helps reduce clogging. Now, these columns have a 600 bar limit, but most methods can be run on a 400 bar system. This slide shows how easily transferable methods can be done. The upper tray shows the poroshell 120 ECC18 and the Eclipse Plus C18 in the same dimensions. As you can see, we're getting about 90% of the efficiency with roughly half of the pressure. Now, what if the C18 column that you've got doesn't work? Well, then you have the options of moving on and using selectivity. Now, selectivity can be used to help. I'll show how selectivity can be used in method development, and also do some comparisons between totally porous and superficially porous particles, show how our alkyl phases can be used for selectivity, what the effect of the chain lengths would be, and perhaps also the end capping. We'll also look at some applications with phenylhexyl and then our new bonus RP phase. Then I'll have some conclusions. Typically, in a method development scheme, what you'll want to do is you'll have several different things to change. This is sort of a simulation that that we worked out and using the resolution equation. As you can see, the selectivity, or alpha, is the parameter that is most impactful on resolution. Now, within that, you can change either the bonded phase or the mobile phase, and these tend to give you differences that will dramatically change your chromatography. While plates are easiest to increase, that is a particle size or a or length of a column, this actually makes the greatest impact. Now, my first slide I want to show is a comparison of our Eclipse Plus C18 and our Horashell ECC18 using an acetonitrile water ammonium formate mobile phase at pH 3. And in this case, I've run about 90 different compounds on a generic gradient that's listed below. And as you can see, we get excellent correlation between these two things. Slope nearly 1 and an R-squared value of 0.9967. This basically indicates that the columns perform almost identically. Now, this experiment was carried out using 7 other conditions for a total of 8 across a pH range of between 3 and 6.5 using both methanol and acetonitrile. And we find very similar results. Now, here's a more complicated analysis. In this case, we have a group of analgesics, and we're running gradients using a 3.5 micron, 1.8 micron, and a 2.7 micron Horashell column. As you can readily see, the elution pattern is very similar. The peak capacity is also quite similar as well. Now, this type of analysis would represent how one would transfer methods across different organizations depending on what type of equipment and needs they have. Now, the last compound on here is ibuprofen, and that's the lead diluter. And now we'll look at why one would choose to use a different type of column for selectivity differences. In this case, we're comparing a C8 to a C18. And this, as you can see on this correlation graph, we have a lower slope, 0.91, which would indicate being less retentive. But the R-squared value is quite similar. There's a 0.9946, which indicates that there's very little difference in selectivity. Now, why would you want to use this? Now, in this case, we have, I show an example of ibuprofen. Ibuprofen was the last eluting compound of that previous chromatogram. And so in this case, you might want to, in the USP method, you might want to be able to elute this with a little bit earlier or with a lower amount of organic and a higher amount of buffer. Now, as you can see here, we take the USP method for ibuprofen, and it's an oral suspension, and reduce the time from about 20 minutes per analysis down to about 2 minutes. Now, another type of selectivity that you can achieve is using the end capping. In this case, we compare our ECC18 to our stable bond C18 Horashell columns. As you can see, the correlation graphs are quite similar again, but in this case, we see that by using just pH differences on the stable bond column on the left and the Horashell ECC18, the end cap column on the right, we can achieve different types of selectivities, primarily looking at bases. And as you can see, the bases are above the line. Now, what other types of selectivity can you achieve on this? This is a separation of some endocannabinoids. And as you can see, we achieve a dramatically different elution order on the stable bond C18 column than we do on the ECC18 column. This can be quite useful for a number of different things. For example, if you have a higher amount of one compound in one, you might be able to rearrange the order of elution and get a little bit better selectivity or less interference in loading. Now, phenyl columns is another new phase that we're introducing. In this case, using acetonitrile, the slope is much weaker than it is using, the interactions are much weaker than you would see when you would use methanol. And in fact, we see an even more diminished interaction than we do on the C8 column. Now, the in fact, using acetonitrile, it looks surprisingly like a hydrophobic type separation that you would see on the C8 or C18 column. But when you switch to methanol, you get a more broadly distributed number of compounds, both above and below the lines. And in fact, you also get a stronger interaction with a slope of about 0.92. Now, this type of separation can be used very easily here. And in this case, we're looking at a group of azodide degradants, and using just a simple generic gradient between 5 and 100% methanol over 10 minutes, we get an easy separation of all 9 peaks, whereas with the bonus RP, we get several coelutions. The ECC18, we get many more coelutions, but in fact, we get a very different pattern each time. Bonus RP is another unique phase that we've got, and as you can see in this case, using acetonitrile or methanol, we get a very different pattern and different elution grouping. The hydrophobic subtraction models and most other data like that shows this type of column when totally porous to be one of the most orthogonal columns around, and we've continued that orthogonality with our porous shell phase. And here is here's an example of use of the porous shell column, bonus RP column with this. And as you can see with this group of beta blockers using an ammonium formate buffer, we get actually the best peak shape of any of these compounds and a little bit earlier elution and probably the best separation. So in conclusion, column selectivity can be a very useful tool for the separation scientists. It's very easy to change this. So in fact, if you've worked out some of your mass spectrometry transitions, you can actually very simply track these things using a different column, or by switch between multiple columns, as I usually do, using a Valving solution. The porous shell columns are designed to have the same selectivity as our totally porous phases, and they're available now in ECC18, stable bond, ECC8, and soon phenylhexyl bonus RP, SBC8, and SBAQ. We expect to see elution order changes, groupings by chemical characteristics, hydrophobic subtraction, hydrophobic, electron donating, and pi-to-pi interactions. In fact, and also we see with some of our columns, we see dramatic peak shape improvements with your chromatography. My contact information here is shown below. And if you want to see more information on our porous shells, you can either type in this rather long email address or just go to Google and type in porous shell 120. Thank you for your attention.
All right, thank you, Bill. For those of you who may have missed my opening remarks, today's webinar will be available for viewing on Lab Manager's website, which is www.labmanager.com. And we will also be sharing the email addresses of all our speakers in our final slide. You will not be able to download a copy of their slides from our website, so I request that you reach out to them directly if you need a copy of the presentations. And please remember, you can send your questions or comments anytime by typing it into the question box that appears on your screen. So let's now turn it over to our second speaker, Douglas McCabe, who is a Senior Marketing Manager in Chemistry Commercial Operations at Waters Corporation. Doug joined Waters in 2001, and he has been involved in the UPLC technology since its inception. He is responsible for developing chromatographic strategies and solutions to facilitate the growth of UPLC. And throughout his career at Waters, Doug has been instrumental in defining, developing, and commercializing some new particles, chemistries, columns, and products for both HPLC and UPLC. Welcome, Doug.
Thanks, Tanuja. Good day, everyone. The title of my presentation today is How to Best Utilize Existing HPLC Systems While Your Company Transitions to UPLC. But before I get into the heart of my presentation, I think a couple definitions are in order. So first is, what's this thing that Waters calls UPLC? Well, as we define it, simply and scientifically, is UPLC maximizes the performance of small particles when they're packed into small columns that are designed specifically for use on a low band spread or low dispersion, high pressure compatible LC system. The idea is that to minimize the band spread, maximizing the resolution. So one of my colleagues calls it, it's a peak generating machine that happens to be an LC system. What are the benefits of UPLC? It has a sort of a misnomer of being strictly a speed instrument, but that's not the case, and I just want to clarify that before I get into the heart of my presentation. So UPLC, the benefits to chromatographers are it can provide the same information, no better, no worse, as an HPLC system in less time, or, if you prefer, more information in the same amount of time. You get to choose. And I want to try to illustrate that over the next couple slides. So shown here are, as you can see, 4 chromatograms. I'm going to call 3 HPLC separations on the top, and the reason I'm calling them that is the size of the particle and the length of the column. These are all 2 millimeter IDs, all run on the same system. So the topmost chromatogram is a 5 micron column with a 150 millimeter length. The green, or the second one from the top, is 3.5 microns, 100 millimeter length. The third is a 2.5 micron particle column, 75 millimeters in length. Now, as you can see, all 3 of these chromatograms, they look similar. The difference, of course, being the flow rates and the dimensions of the column. However, the resolutions remain the same. Down on the bottom, we have what I call a UPLC separation. And I'm calling it that because, as it's been defined, is a particle of less than 2 micron. And it's a 1.7 micron particle column, 50 millimeters length. All 4 of these columns have one thing in common. That is the same length to particle size ratio, or as we call it, L over dP. So visually, these chromatograms look the same. But where are they different? The difference is, how long does the researcher have to wait before they get the results? With that HPLC column, probably one of the more common configurations in the marketplace, you'll have to wait 10 minutes. For a UPLC column on the bottom, you're going to get the same quality of data, the same peak height, the same signal to noise, the same everything, but you only have to wait 66 seconds. So that's where it's the speed message, but it's speed without compromising the chromatography. Now, what if speed isn't important? What if the bottleneck of your laboratory is elsewhere? Well, the other option you can get with chromatography, if you're happy with the analysis time, you can increase the information or the peaks per unit time. And I illustrate that on this slide. The top chromatogram is a HPLC column packed with 5 micron particles, and 70 peaks are detected, and we get a peak capacity of 143. Peak capacity, for those of you who aren't familiar with that term, is the theoretically how many peaks can be separated during the course of a gradient. Okay, so it's like the gradient version of efficiency in an isocratic separation. On the bottom, as you can see visually, as we can confirm numerically, there's a lot more information on that bottom chromatogram. Each of the separations is a 60-minute separation. This is a peptide digest, which is a very common analysis time. But not only are the big peaks bigger, but more importantly, the little peaks are there. The little peaks are in that top chromatogram, but they're buried underneath. And then one more definition, which I'm going to spend sort of quite a bit of time talking about a little bit later, are what are these things called extended performance, or XP columns. They are fully porous particle columns that are compatible with pressures up to 18,000 psi that sort of bridge the gap between what I call UPLC and what you call HPLC. So as they're designed to withstand any pressure you can throw at it. 4.6 millimeter IDs kind of designed for an HPLC or UHPLC system, and the smaller internal diameters with a UPLC system. We have flexibility in the configurations. In fact, there are over 160 combinations of columns, lengths, and chemistries. So as I mentioned, 2, 3, 4.6 millimeter IDs, lengths from 30 millimeters to 100, 14 fully scalable stationary phases, which means that we have sub-2 micron versions, the 2.5 micron XP, 3.5, 5, and sometimes 10, all seamlessly scalable. And the 14 chemistries are described below based on 3 different particle substrates. Think of it, it's something for everyone. A lot of these chemistries, as the previous speaker had mentioned, that are designed to do different things and to complement each other. Now, I think I will be the only person today that's probably going to be speaking about fully porous particle columns. So I just want to put this in context. There are 5 Van Dienter curves here, which are just a way that we column manufacturers and researchers take a look at the efficiency of a column. These are non-reduced, which just means these are this is the height equivalent of a theoretical plate, And as you can see, the efficiencies of the 3 porous and the 2 superficially porous particle columns pretty much look the same. Back pressure-wise, there's no magic, no difference here. The pressure in a column is based upon the particle size, to some extent the distribution, and how tightly or loosely the column is packed. So in a sense, we're in that same ballpark with these particles as semi-porous particle columns are. But the difference we have a little bit is a much wider choice of chemistries and seamless scalability from UPLC up to isolation and purification. So with that couple of minutes of definitions, let's get into the heart of the presentation. Chromatography has changed. Okay, it's no longer the mature science that it was destined to be up until, let's say, the early 2000s. A lot of organizations have realized that there are better ways to move their work through the chromatographic laboratories. But they're basically given a choice now. Do you go down the higher pressure, smaller particle route, or do you try to stay somehow with your HPLC or UHPLC system? So we're asking people to make a choice. So this has forced customers to have to evaluate how to best utilize their existing HPLCs, their laboratory full of LC systems, while they continue to look at transitioning to newer, more modern systems. And they have some choices, right? 2.5 micron, 3.5 micron particle columns, and the core shell or superficially porous particle columns that you're going to see quite a bit about today. So there's some challenges that have to be met. And what are some of those challenges? Well, if we look at it, let's say, by the number of systems that you have within your company, you probably have a lot of HPLC systems of various ages, some UHPLC systems, and you may even have dipped your toe in the water for UPLC systems. So what do you have to do? It's one thing that you have a scientific LC platform, but what about how does this impact your work? So the challenges are in HPLC, you need to utilize all those LC systems and start to future-proof your laboratory and have a transition strategy to modernizing your chromatography. In the UHPLC world, larger ID columns are still sometimes used and recommended to overcome system dispersion or band spreading. That's the enemy of efficient separations is that volume after the injection before the end of your detector. And still thinking ahead to different LC systems. And in UPLC, the biggest roadblock is really, will I have to revalidate? And in some cases, for simple chromatographic separations, a lot of compendial separations, reduce your back pressure where you can when you have resolution to spare. So how can we address these challenges? Well, here on this slide, it's going to tell a nice story here where we're looking at some flexibility, I guess is going to be my theme for today. Is on the top, we have a 150 millimeter length column packed with 5 micron particles run on an HPLC system. It's a 40-minute gradient separation. Now, what we're doing here is on that same HPLC system, right, the same HPLC band spreading and pressure limitations, we're going to run this extended performance column. 75 millimeter length, 2.5 micron particles. Same length to particle size ratio on this column as the one on the top. So we get the same separation. The difference is how long do we have to wait to get that data. So we get the data in one-fourth the time. Now let's take the same column but run it on a different system. So in this case we have an Acuity UPLC H-class system. Again, 4.6 millimeter ID, and again, the chromatography looks virtually the same. The minor differences in retention time are the minor differences in the system volume, because this is a gradient. And then lastly, if we migrate or take this method and rerun it with a UPLC column as defined by the particle size, 1.7 micron, on 2 different UPLC systems, we get, again, the same chromatography top to bottom. You just don't have to wait as long to get that information. So that's flexibility within the systems, flexibility with particle scalability. And then the last example I want to show you is something that I think a lot of you can identify with. Let's look at some running a compendial, a USP method. This is for a birth control pill, isocratic separation of levonorgestrel and ethinyl estradiol. And what we're going to do is we're going to go through a couple types of method migrations or method transfers, and we're going to take a look at the results and try to tie everything together at the end of the presentation. So here we have the compendial isocratic separation as dictated by the USPNF. So it's using a 150 millimeter length column, 4.6 millimeter ID, 5 micron L1 column on an HPLC system. The upper right-hand corner of the screen, I have the system suitability tests. We all know what that means. It has a resolution between the two analytes of interest of not less than 2.5, and again, a inter-injection precision of not more than 2% RSD. A lot of the formulas on the bottom, those will be for just to let you know that a lot of what I'm going to show you in the next few slides is predictable with some basic calculations. Things down here, that length to particle size ratio is here. That's the resolving power of the column. The resolution, which is proportional to the square root of the efficiency, or N, or number of plates. Your optimal flow rate is inversely proportional to the particle size. That means the smaller the particle size, you should increase your flow rate, because that Van Diemter curve I showed you earlier, the flat spot moves to the right. And then the runtime here, everyone remembers this from when they first touched a chromatograph. The longer the column, the longer the runtime, the faster the flow rate, the shorter the runtime. So that's how all this ties together, okay? So that's just to mathematically check things as we move along. So let's do, on this slide, what I did a couple slides ago. Take that same compendial 150 millimeter length column separation. Now run it on a 75 millimeter length, 2.5 micron particle column at a milliminute. Now, if you remember from that optimal flow rate rule that I gave you on the previous slide, the flow rate here should really be 2 mils a minute. From 5 to 2.5 is a factor of 2. You should multiply that by your flow rate, assuming the same column ID. But we can't do that. Why? Because of the pressure. So we're doing it in a milliminute. But we still get pretty good results, and we managed to get half the runtime. In order to run a little bit closer to the optimal linear velocity, what we had to do on the bottom chromatogram is shorten the column length. Now it's only 50 millimeters. So when you do that, you can see the resolution of 5.2 versus 6.5. The reason it's lower is because that length to particle size ratio over here, length divided by particle size, is a unitless term, 20,000. So that's basically 50,000 microns divided by 2.5 microns, which is 20,000. The original was 30,000. So we're still able to get some throughput benefits, and both of these changes are compliant with USB chromatography 621, which dictates what you can and can't do to a method when the system suitability test fails. And a couple of the parameters I'm pulling out in this text box on the right is the length of the column can be adjusted plus or minus 70% as compared to the method indicated in the monograph, and your particle size can be reduced by up to 50%. So both the mathematics works out. And then the last chromatogram I want to show you today, or the last two, is let's ignore a transfer. Let's say that if we were going to develop this method all over again and we wanted to get the best separation possible, you migrate or run the separation on an H-class system. So now we're able to use 2 millimeter ID columns, which means we get to use less mobile phase, and 0.42 mils a minute is the geometrically scaled flow rate, which means we've adjusted the flow rate based on particle size and column ID. We have a pressure of over 4,000, runtime of 2 minutes, which means that we've cut our runtime down by 75%. And we get almost, basically a little bit better resolution. But if we really want to get the same separation that we got in the compendial method, but we don't want to wait, we're not very patient, you run that again on a UPLC column. Again, that length to particle size ratio here is 30,000 or 28,500. The flow rate of 0.61 mils a minute is faster than the 2.5 micron particle column because the particle size is smaller. That generates more pressure, but we get our runtime now down to less than a minute. So now we have a 90% savings in time, but we're getting the same information that we got in the compendial method, but you get to go 10 times faster. So in closing, productivity and throughput are improved on any LC system by using fully scalable UPLC compatible XP columns. So in this case, we're not forcing anyone to make a choice. The methods could be transferred within the higher dispersion HPLC systems using a larger column volume, a 4.6 millimeter ID. You can also move this or migrate or develop a method using smaller ID columns on a UPLC system which has lower band spread or lower dispersion. And as I showed you earlier, you can also use the same 4.6 millimeter ID columns that you're using today. And that these columns offer what we call a strategic bridging strategy between the present, or let's say of HPLC, and the present and future, which is UPLC. And this is compatible with all LC systems, whatever pressure you have, 14 chemistries, a plethora of IDs and lengths, and enables you to get the most out of your LC system today while you transfer to UPLC or UHPLC tomorrow. So for that, I thank you for your time and attention. For more information on these particular columns, www.waters.com/xp. It's sort of like a one-stop shopping for everything where you can download our brochures and care and use guides and some application notes. So thank you.
Great. Thank you, Doug. Our third speaker today is Stephen Luke, who joined Thermo Fisher Scientific as their LC columns product manager in the UK in 2011. He started working with liquid chromatography in a pharmaceutical analytical development lab during the mid-1980s, and since 1991 he has held various roles in R&D, marketing, sales, support, and service for leading organizations in the separation science industry. So welcome, Stephen.
Thank you very much. Hello, everybody. My quick presentation today. Title takes the form of we easily speed up separations using solid core HPLC columns. What do I mean when I say solid core? Also a phrase under other names today, superficially porous, core shell, fused core. It all means the same same basic thing, and it's shown here on Mars appearing in the 21st century. Do we care about solid core materials allow higher, a couple of reasons behind quickly shown on this slide here. Reductions in the eddy diffusion, the amount of the way in which peaks get broader due to, if you like, allied molecules meandering in the Van Diemt C2. That's related to the amount of time allied molecules take getting in and out of the stationary phase particles in simple terms. So some features of the column design result in more efficient chromatography, and indeed more efficient chromatography at higher flow rates. Without a quick view of a Van Diemt curve and a pressure plot, which are fairly traditional ways of looking at how columns behave. Something a little bit different is to look at a plot of impedance. So this impedance plot, the E value, basically a low impedance indicates chromatography that's performed at a low pressure with fast run times and high efficiencies. So in the little formula you can see on the screen, P is pressure, T is retention time, the capital N is efficiency, and the fun-looking N shape is solvent viscosity. So a solid core material indicated by the purple line on this plot gives you a much lower impedance than any fully porous material. In fact, we see 3 fully porous materials shown higher up on the plot in 5 micron, 3 micron, and sub 2 micron diameters. So if we're interested in fast chromatography performed at HPLC style back pressures with high efficiency, then we're interested in low impedance chromatography, and we're interested in solid core materials. That said, let's look at some evidence of this in work. So we're going to see examples of how we took a chromatogram run on a standard HPLC column and saw how much faster we could go using a solid core column. Columns that we used in the work we're going to see, a fully porous column was a high precision gold column. shown on the left here, nice picture for you to look at. Specifications are on the screen together with a radar plot showing the detailed phase characterization. And the solid core column that we used was an AccuCore RPMS column. And again, specifications and phase characterization radar plot shown. So here's our standard chromatography. Performed on a fully porous column. It's a 5 micron particle diameter material, 15 centimeters long, so 150 millimeters with a 4.6 millimeter ID. Conditions shown up in the top left of the screen. So water acetonitrile gradient over 10 minutes, 30 degrees Celsius temperature, 5 microliter injection volume, and 1,000 milliliters per minute flow rate, or 1 milliliter per minute. You can see the chromatogram down at the bottom of the screen, and on the upper right, some parameters we use to characterize this chromatography. So you can see the retention time of the last peak at just over 9 minutes. The selectivity, or the basically the ratio of the retention factors for the first 2 peaks as the selectivity value. The peak width for the last peak in minutes, the resolution between the first 2 peaks again, sensitivity, which is basically the signal to noise ratio divided by the injection volume in this case. And then we've calculated the amount of solvent used per run, which is the total runtime multiplied by the flow rate. So in this case, a 17-minute runtime, including gradient re-equilibration, multiplied by 1 mil per minute flow rate, and finally a back pressure down there at 64 bar. So this is probably pretty standard-looking chromatography to a number of people, but the title of our presentation was how can we go faster? So what can we do? Well, if we're going to look at working with a different column, perhaps different column dimensions, certainly a different column particle design or different stationary phase particle design, then we need, as the previous speaker mentioned, to scale some of our method parameters. We need to keep with the linear velocity constant between the original and column and the new column dimensions. We need to keep the injection volume ratio to column volume ratio constant. And if we're running a gradient, we need to keep the number of column volumes constant in each segment of the gradient. On the screen here, you can see the calculations used. They're all pretty straightforward. But the good news is that there are online calculators that can do this for you. I give an example of one that's available for here, but there are a number of others available online. You basically enter your starting conditions, your starting method, column dimensions, etc. You enter your target column dimensions, and the system returns for you what your new method parameters should be. So here's a quick example of the converted method. So this time, rather than a 10-minute gradient, first of all, I should say this is performed on a solid core column with a 2.6 micron particle diameter. It's 100 millimeters long with a 2.1 millimeter ID. So using the online calculator, that tells us that we should be using a flow rate of 400 microliters per minute. That's a pretty familiar value from the previous presentation. An injection volume of 1 microliter, a gradient time of 3.5 minutes, and our total run time, including re-equilibration, will be 6 minutes. You can see the chromatogram down the bottom of the screen, and what did we get in terms of results? Well, our retention time is now 3.6 minutes. The separation between first 2 peaks, selectivity of 1.28, peak width 0.072, and I'll let you read the rest of the numbers for yourself. We have a quick look at the comparison there. So up above the original fully porous chromatogram, down below how much faster we've managed to go using the solid core column. Now, of course, some of the reduction in retention time is because we're using a slightly shorter column. So we've gone from a 15 to a 10 centimeter column. And indeed, you can see a significant reduction in the amount of solvent used. And part of that is because we've moved down to a smaller column internal diameter. Have a look at the change in performance between fully porous and solid core. So we go from a 9-minute retention time to 3 minutes. Selectivity remains very similar. Peaks become much sharper, so a much narrower peak width. Previous presenter talked about peak capacity. So peak capacity calculation is based on the column, on the peak width value. So we have a much better peak capacity in the separation. Resolution improves slightly. Sensitivity improves a lot. And our back pressure is higher, but still at 260 bar, we're still definitely talking about an HPLC style back pressure. So no requirement here for specialized instrument hardware in terms of pressure rating. So that was relatively straightforward. We used our online calculator to come up with a set of new method conditions based on the use of a solid core column in different dimensions. But can we do better? Can we go faster using the solid core technology? So I'm going to show you a couple of options that we tried out. The target for what we were trying to achieve was the shortest possible retention time with adequate resolution and an HPLC style back pressure. So here are the options we looked at, numbered 1, 2, 3, and 4. In option 1, we reduced the column length from 100 millimeters down to 50 millimeters. Again, using our online calculator, we worked out that we were going to need to change our gradient time, basically to half of what it was, so down to 1.8 minutes, because we have half the column volume with half the length. In option 2, we look at increasing the flow rate, so from 400 microliters a minute up to 600. So we're moving away from the optimum value, but one of the characteristics of solid core materials is that as you increase the flow rate, you don't see large decreases in efficiency or large increases, let's say, in the peak width. And because we changed the flow rate, we need to change our gradient time, and that's shown there. In option 3, we increased the flow rate again, up this time doubling it to 800 microliters from the original 400. Again, you can see a change in the gradient time. And finally, we had to go at changing the temperature, so moving from 30 degrees Celsius up to 40. So a selection of fairly straightforward changes made to the method. And here's what happened. So by going to a 50 millimeter long column, conditions shown on the left and results on the right, down to a 2.19 minute retention time, a peak width of 0.056. Highlighted in red is the resolution value, 1.53. Question we'd ask ourselves is that the adequate resolution we were looking for? Nice low back pressure, 141 bar, because we're using a column that's half the length of the original. Here are the comparative chromatograms showing how much faster the shorter column is and how much less solvent we're using, because flow rate stays the same, because of course we're using the same internal diameter for the column and the same particles, but shorter run time. So down there at only 1.2 milliliters of solvent used. And here the parameters compared. So from 3.6 minutes with the 10 centimeter column down to 2.19 minutes. Selectivity, in fact, improved somewhat with the shorter column. Peak width down quite a bit. Resolution reduced. The question is it still adequate? Sensitivity is not quite so good here. Solvent use lower down, and back pressure nice and low. Okay, option 2, increase the flow rate. So this time moving up to 600 microliters per minute. We're back at the 100 millimeter long column again. So there's chromatography. Also ran at 800 microliters per minute. So we're going to present these two flow rate options together. I'll skip on to this slide, which shows the comparative chromatograms. Now, although we're reducing the runtime each time, because we're increasing the flow rate, we make no change to the amount of solvent used per run. So it stays at 2.4 milliliters. But if we compare our performance, so the original at 400 microliters a minute, and then the 600 and 800 compared to it. So you can see at 600 we get down to a 2.5 minute runtime with a 0.058 minutes peak width, and pressure of around 344 bar, so on the upper range of traditional HPLC back pressures, if you like. At 800 microliters per minute, we have a 2.14 minute retention time. Very nice narrow peaks at 0.053. One query here might be, is 440 bar a acceptable HPLC style back pressure? For newer instruments, perhaps. For older style instruments, maybe not. And our very last option we tried, run the column at 40 degrees Celsius. So don't mess around with flow to column length, just try and run at a little bit higher temperature. So here are the conditions, here are the results of that test, here are the comparative chromatograms. Because nothing changes, we use the same amount of solvent. Here we can look at the comparative results. So retention time, better, so faster. Selectivity, not as good. Separation in terms of retention time or retention factor of these peaks. Peak width is down. The resolution at 1.37 is probably not acceptable. So although temperature can be an interesting factor to play with, in this case probably a little bit too warm because we don't quite get the resolution we were looking for. Notice though what it does to our back pressure. An interesting feature of increasing temperature is it will bring back pressure down quite significantly, and here we've taken it down from 260 to 194 bar. So in closing this presentation, which is our best option? We were looking at the best possible option to go faster using solid core compared to traditional chromatography. Which is our best option? Is it the short column? Is it the slightly higher flow rate? Is it double the flow rate? Or is it the higher temperature? And if you accept 1.53 as an acceptable resolution, then I think you have to say it's the shorter column. If you accept 440 bar, you might consider it's doubling the flow rate. But the only answer we have here in which we have no red issues, if you like, is running at 600 microliters per minute. So higher than optimum flow rate, but still not having a negative impact on the performance. That's everything I have to say. Hope it was useful, and here are my contact details.
Thank you, Stephen. Our final speaker today is Dr. Wayne Wei, who is the Marketing Manager for HPLC and GC products at Sigma Aldrich. Wayne joined Supelco Sigma Aldrich in the R&D group in 2004, but he took the position of Market Segment Manager for HPLC in 2005. His current research interests include method development and validation, as well as materials identification, in which he has served as an expert witness in state and federal codes. So we would like to hear more about that too, Wayne, whenever you have a chance. Thank you and welcome.
Thank you. And thank you all for attending and sticking around for all 4 talks. Quite interesting. And what I plan on presenting today is the topic of choosing the correct dimension fused core HPLC column when transferring methods from 5-micron columns. So there's been a lot of good talk today. 2 of the previous talks were on superficially porous columns, but I want to take that topic and present, let's see here, my slide is not advancing. There we go. I want to take just one actionable item and present that to you, and that is the transfer of a method from a 5-micron column to a 2.7 micron column, and make that very simple. And why is that important? Well, fused core HPLC columns have been recently introduced to the market. 2007 was when the fused core column was introduced at PepCon. And many users have considered switching from traditional 5-micron columns to the 2.7 micron fused core column for performance improvements on traditional instruments. And when I say traditional instruments, I'm meaning mostly HPLC systems. But little data has been discussed on choosing the correct dimension for a smooth transfer. Why might one consider using a fused core column versus a 5-micron column? This type of data has been shared in many formats, so I'll briefly review it. And what we're looking at is a Van Dienter plot of a variety of particle sizes. And the main points of the Van Dienter plot is that the lower on the y-axis, or the H term, you have a higher efficiency separation. And the x-axis is your mobile phase velocity, or your flow rate. So there's two phenomena that happen as you go from a larger particle to a smaller particle, and that is, one, the value of the H term decreases, so you are getting more efficient separations, higher resolution separations, but the other phenomena that I will address in this presentation is the flatness of the Van Deemter term, meaning there's a larger variety of flow rates available at this high performance operation. Mostly going to higher flow rates is conventional, but there's just a variety of flow rates that are available at a higher optimum performance, whereas if you look at the 10 micron column, it's a very narrow bandwidth. So how does this happen? How does the fused core mimic a sub 2 micron? Certainly performs better than expected only based on its particle size. And that is, the fused core provides efficiency of a smaller particle but pressure of a larger particle. And you can see there's 4 references there. I'll show those on the last slide that point to that. And there's a couple ways you can look at that. One is the short diffusion path improves the mass transfer, certainly especially at higher molecular weight and faster flow velocities. So if we look at this simple two-dimensional diagram of a traditional 5 micron fully porous column, you have a potential diffusion path of the totally porous particle of 2.5 microns. And if you look at the architecture of the fused core column with a 1.7 micron solid impermeable silica core and a 0.5 micron permeable silica shell, you can see that that diffusion path in and out of the particle, which is how chromatography works, is much reduced. So that was a look at sort of a one particle versus one particle comparison. But now if we look at a collection of fused core particles and compare that to a collection of your typical porous 5 micron column, there's a let's call it a macro effect, and that is the particle size distribution is significantly narrower with a fused core column, approaching monodispersity. So with your typical porous column, you have a standard deviation of about 15 to 20% of the mean, where with a fused core column, you have a standard deviation of about 6% of the mean. And that has a secondary value to improving the performance in terms of peak width. It also makes the column more rugged, which I won't discuss today in this short presentation. But the reason that this can make sharper peaks, and a slide like this was shared earlier in the talk right before mine, so I won't go into much detail, but you can decrease the A term in the Van Deemter, which is the uniformity of flow paths. So with a narrow particle size distribution, say the options for different flow paths for an analyte are reduced, and that will give you a narrower peak, where if you have a broadly dispersed particle size distribution, the possible flow paths are increased and you will get broader peaks. So back to the point of the first slide is, how are we going to transfer a column or a method from a 5 micron traditional column to a fused core column? Well, the first thing I would always recommend someone to consider is, what is the purpose of changing to a fused core HPLC column? And there could be a variety of reasons that are considered, but I'll touch upon the 2 most common ones today, and that is A, to increase speed or throughput, so have a faster analysis, or B, increase resolution. And I think this is a very important point that's often overlooked, is that you really need to come to an understanding what is your purpose in doing that, and address that first. So if we take the first topic to start, increasing speed or throughput, the transfer from a 5 micron column to a traditional fused core column, certainly there are many calculators that you could use and many calculations to address this, but what I'm going to do is make it very simple, and this is the way I would recommend that. So what you have is, across the dark blue bar, is your current dimension 5 micron, and I've chosen 3 very common dimensions, and there could be others. So we have a 25 centimeter by 4.6, a 15 centimeter by 4.6, and a 5 centimeter by 2.1. And again, with today's talk, we don't have time to examine all of those options, we're just going to look at the very first box. So if you have a 25 by 4.6 method on a 5 micron and you're interested in increasing speed and throughput and transferring to a fused core, my first choice recommendation is a 10 centimeter by 4.6 millimeter ID column. And the next slide will show you why. If we look at the efficiency of columns of various dimensions, or various lengths I should say, within a 5 micron particle, you'll notice that the 25 centimeter column with a 5 micron particle has the approximate efficiency of 24,000 plates. If we look at a fused core column with the same type of plot, the same type of particle, column length dimensions, you'll see that the one that most closely matches that is the 10 centimeter column, which again also has an approximate efficiency of 24,000 plates. So again, what my recommendation is just change that column. My initial recommendation would be not to change your flow rate, not to change your sample prep procedures, not to change your injection volume. All of those certainly could be optimized further, but that would not be my first recommendation to do. So if we look at the top chromatogram, data collected on a standard Agilent 1100 HPLC system, you can see we have a conventional C18 25 centimeter by 4.6 millimeter ID, a 1 millimeter flow rate. You can see the efficiency of the last peak is approximately 22,000 plates and a standard back pressure of about 1900 psi. If you look at the bottom left, by simply just dropping in this new column and changing nothing else, we have a, again, maintaining the same flow rate to start. We have a efficiency of about 22,000 plates again, so the efficiency remains the same, and our pressure is just modestly increased from 1900 psi to 2400 psi, and we've shortened the runtime from approximately 40 minutes down to 10 minutes. Now certainly another way to improve speed is to increase your flow rate, and again that's something that can be done on a fused core column or other small particle columns because of the flat Van Deemter that we discussed earlier. So here, just by simply increasing the flow rate by 50%, so now we're at a flow rate of 1.5 mils a minute, we've cut the runtime down again to about 7 minutes, and again, quite a manageable pressure of 3,600 psi. So tackling the second topic, increasing resolution, transfer from a 5 micron traditional to a fused core column. Well, this one's quite simple, and as you can see, I have the same current dimensions listed for your 5 micron, and the first choice fused core dimension is I would recommend transferring to the exact same column dimension. Now what you'll see is there's one aberration there, and that is with the 25 by 4.6 column, I do recommend switching to a 15 by 4.6 column. That is because the 25 by 4.6 column is not available and would provide too much back pressure under normal operating conditions for an HPLC. So again, without time to go through all three of these scenarios, we'll pick one of them and take a look at that. In this case, I've chosen the 5 centimeter or 50 millimeter by 2.1 millimeter ID comparison. And in the top graph, we have a Discovery C18, so a standard totally porous 5 micron column operating at a flow rate of 1 milliminute on a 2.1 micron, so certainly a high flow rate, but used by many in this type of environment. And you can see the efficiency in this particular example on the same Agilent 1100 system is 2,400 plates, and by simply swapping to the Ascendus Express, same column dimension, same flow rate, we have efficiency of about 7,600 plates on the last peak. Now looking at one last example, and that is a conventional C18 10 centimeter by 4.6 millimeter ID, 5 micron. We have a runtime of about 10 minutes, and the plates are about 14,500. Here switching to the Ascendus Express C18, we do gain a little bit in terms of speed. That is not caused by the particle architecture. It's caused by comparing a high surface coverage porous particle, the 5 micron, to a less surface area Ascendus Express. So we do gain a little bit of speed, but that wasn't the initial design in the experiment. But you can see we have very sharp peaks with an efficiency approaching 30,000 plates on this 10 centimeter by 4.6 millimeter ID column. So in conclusion, hopefully I presented a very simple strategy for transferring methods from a 5 micron traditional column to a fused core column on your traditional HPLC instruments. And again, I'd like to stress, I think it's important to determine the primary goal before the transfer. That may seem obvious to some, but not all do that. And please just follow the easy steps provided. If you have any additional questions on this topic, my email contact will be provided on the last slide. So again, these are some references and acknowledgments I had mentioned earlier in the talk. I won't dwell on this slide, but if you're interested in seeing these, you can again contact me and I can provide you those citations. Thank you.
Thank you, Wayne. As you can see, you now have all the email addresses for all our speakers on your screen. If you do need a copy of any of their presentations, please feel free to reach them directly. So with that, let me get to some of the questions that have been sent in. Well, let's start with this one, which is, and I'm not sure if this is a misconception, but are newer models of LC columns significantly better when it comes to developing faster LC methods? Can you comment on this and let us know if this is true or false? So are the newer models, significantly better for developing faster LC methods?
Actually, could I take that call?
Yes.
This is Bill Long.
Oh, Bill. Okay.
Okay. One of the things as a column in column manufacture, we usually benchmark existing columns before we introduce a new material. In general, we're trying to make products better. Or so your choice of I agree with you in that if you were to look at a newer material when you're developing a newer method, that's usually a very good idea.
Okay, great.
This is Steve Luke from Thermo. I think the question said were newer columns better for developing faster methods. I think the whole idea behind UHPLC and behind solid core is that more efficient particles allow the use of shorter columns and therefore shorter runtimes. So yes, newer technology allows faster runtimes. I think that's been a key part of a number of presentations today.
All right. Thank you. Anyone else would like to add to that before I move on?
Sure. This is Doug at Waters. I agree with the previous two answers. Along with the particles getting smaller, what else has improved, especially at Waters, and I'm sure my my counterparts as well, is the knowledge behind how well a column can be packed has greatly increased in the way columns pack, the robustness, even better ways to test of various column packing, because the particles are only as good as the final column, which is what does the separation. So yes.
Okay, great. All right. Well, moving on. Now, column lot-to-lot reproducibility. I think this is more important for GMP type applications. So, would you like to comment on how much variability are you seeing in the columns that you supply?
This is Steve from Thermo. I can say that one of the things that we're doing now is a very detailed characterization of each lot of material, whereas in the past batches of packing material may have undergone a single simple chromatographic test with a basic test mixture. We're now certainly performing a detailed multi-method characterization that looks at things like hydrophobic retention, steric selectivity, secondary acidic and basic interactions. So we have a very detailed characterization on the phases, and that allows us not to release anything that isn't to specification and indeed similar to all previous batches.
That's good to know.
This is Wayne Way from Supelco. I will add a little bit to that question. I do have a unique perspective to that. Before joining Supelco, I managed a CRO, so I was on the other end, the same size as many of the customers. And what I would recommend to the customer, certainly I think across our industry as a whole, reproducibility is improving, but I still think it's important for the developer to do their due diligence and check a variety of bond lots. And I'm sure all the manufacturers, certainly Supelco, will work with anyone on getting a variety of bond lots to examine, whether it be 3. Another thing you may not have considered to ask is maybe to look at 3 bond lots that aren't sequential, so try to get a variety of dates to examine those. Just some advice I might give.
Okay, appreciate that. Anybody else? Okay, if not, moving on to our next comment. We have a walk-up system, and our columns, must be very robust to operation by students who have minimal understanding of how HPLCs operate. So I think just to broaden that out a little bit, I mean, can you all share some tips on how to, increase column life, maybe prevent cross-contamination, and just overall, help in the maintenance of these instruments and columns both? All right, who wants to go first?
This is Doug from Waters. I think I can go first.
Okay.
Basically, to improve the lifetime of any column, the better job that the user can do in terms of having a routine procedure for maintaining, whether it's the solvents or the quality of the sample that goes through the column, can do nothing but improve the lifetime of the column. One of the small prices that one has to pay in going down in particle size is you do tend to have to make the frits a little bit smaller in terms of porosity, which turns them into very good filters. So it's general lab practices would improve the lifetime of any LC column, whether it's UPLC, UHPLC, or an HPLC column.
Thank you, Doug.
This is Steve from Thermo. I would always, of course, recommend the use, where possible, of guard columns or guard cartridges. So if the worst does happen and something naughty gets go down the system, there's a chance that the guard catches it before it kills the main column.
Right. That's a good suggestion.
This is Bill from Agilent, and I'm going back to agreeing with Doug at Waters, primarily because usually we look at lab hygiene as being far more important with small particle columns. 5-micron columns were pretty durable, but having good filtered solvents being used, or buffered mobile phases in particular, the potential for bacterial growth in your buffers is quite high. So you might see things happening with a small particle column that you wouldn't see with a larger particle column. The other thing that's important, I think, as well is the instrument itself. For example, if your walk-up lab uses a buffer, leaving salt in contact with metal parts is not generally a great idea. So you do need to perhaps rinse the instrument and perhaps even make sure that the column is stored properly in a water and acetonitrile mixture between uses, or at least for longer term use.
All right. No, that's all good advice.
One last tip on that, Wayne Way from Supelco, is that usually in these types of walk-up instruments you're using wide gradient swings from virtually complete aqueous to complete organic. And I would just caution to watch both your sample solubility and your buffer solubility through those wide swings, because anything that sort of crashes out could cause some problems.
Okay. I think just as a follow-up to that, there's a comment that are the new generation columns in general, do they have a shorter life? As I say, everything was done better in the good old days. So is that something that's applicable to columns as well?
This is Bill Long at Agilent. One of the things that you might notice is with a 50 millimeter column, you could literally run 1,500 samples in a weekend, whereas a longer column, running a slower flow rate might take a week or a couple of months to achieve that number of samples. So the columns today, in order to get higher performance, we had to make smaller particles or smaller frits, as we put it as well. But the columns in general last have a similar lifetime to what they did in previous years. If not, in many cases, it's a lot better.
Yes, it's Steve from Thermo. We have had some testimony back from customers talking about approaching 10,000 plus injections from some contests. Almost seem like unbelievable numbers sometimes. So I think a statement that column lifetime is decreasing, we don't see supported by customer comments.
Okay.
Yeah, this is Doug from Waters. The mechanical stability, which is just how tightly and how well and how efficiently the bed is packed, of the newer columns is much, much better than older columns. To sort of tie this answer in with the previous question, the demise of these more modern, smaller particle columns usually isn't related to some sort of breakdown within the column or within the particle or within the chemistry. Those are much better now than they were 10 or 15 years ago. It will be some sort of microparticulate or bacterial plugging of the frit, which is usually what causes the column to die, what can be considered by customers to be a premature death.
I see. Okay. All right. Well, here's a comment, and I think this goes back to the issue of the topic for our webinar today. How do you pair the right column with the right application, or what are the criteria that goes into column selection? So the comment is that the cost of LC columns makes it very hard for us to try different columns, which is why vendor input and vendor applications are so important. And I'm sure all of you have something to comment on that.
Well, this is Bill at Agilent. The cost of columns is roughly, it hasn't changed dramatically in the last several years, but one thing that has changed even much more has been like the cost of solvent and getting rid of solvent. So by not taking advantage of new technologies, smaller particles, shorter columns, you could incur greater costs than by choosing to examine a few different columns. It's being able to shorten a method by, and we saw very simple shortenings of 60%, just by going from a 5 micron down to a 150 millimeter column down to a 4.6 of 50 millimeters. You're saving enough solvent costs and also the disposal costs as well to more than justify looking at several columns. So.
Right. But do you work with customers regularly to help them with their method development, or what sort of support do you provide for applications?
Well, I'm actually an applications chemist in the lab, and I do work with customers fairly regularly. One thing that people should always do is start out with a literature search when you're doing method development to start to get an idea about what type of columns that you're having to look at, compounds. But no, we work very closely with customers, and so it's usually a good idea to work with the salespeople that you have in your area, and they actually can help get expert attention to their problems if it's.
Okay. Anyone else has their experiences? Yeah. Okay.
Steve Luke from Thermo. I think there's some great information available online now from a number of different column manufacturers in terms of phase characterization, selectivity mapping, that kind of stuff. So you can really, if you know the way in which you want to discriminate between your analytes, you can do some pretty good research and find out what type of phases could be the kind of ones that will be useful to you.
Okay, great. Anyone else? All right. Here's a question about applications that have been developed for use with mobile devices or smartphones. So can each of you comment on what you may have available in terms of applications for maybe predicting analysis time or resolutions when changing columns?
Sure. This is Doug McCabe from Waters. From the area of selecting a column and comparing different columns, for the iPad we have our electronic selectivity chart where the user can take a look at finding columns that are similar, that are different, selections of columns, types of chemistries by L classification, all available for the iPad. And on the website we have things like the method transfer calculator, an electronic version of that selectivity chart where one can help choose columns, and we also have something called the column advisor where it's let's say help with the application, as it were, where you can the user can select what's important in terms of column performance or what types of application they're looking at, and it will almost be like a virtual salesperson as well.
Oh, great. Okay.
Yes, this is Wayne from Supelco. I can say that we are looking and developing more iPad and mobile device applications. Just recently, we have an app that you can get from the iTunes store, a bioanalytical app, and it helps you choose the right column, sample prep, and mobile phase. So I think more of those are coming.
Okay. Good.
This is Bill at Agilent. We have an online method transfer system that we've had on for several years actually, and there's actually one for gas chromatography as well. We're working on some other types of selectivity and column choice devices as well.
Great. Stephen, anything from Thermo?
Yeah, during my presentation I showed the online calculator, which of course can be run on a mobile device, and we're working on some detailed column selection tools that you'll see available in app format in the near future.
Okay, fantastic. Now, all of you talked mainly about analytical columns. Has there been any sort of new developments on the preparative column side? Do you have any information about that?
This is Doug from Waters. In our isolation and purification columns, virtually every phase that I talked about today, I guess there's 14 of them, they're all available in lab scale preparative columns, which are up to 5 centimeters in diameter. We could even go as high as 10 centimeters in diameter as well. We've had some improvements in the mechanical stability, our optimum bed density design, which is patented, for the columns last a lot longer. So it's all part of a scalability message for us. So everything from a very, very small particle up to 10 micron for lab scale prep, and all of the chemistries are modern, so they're reproducible and metal free, and keep long column lifetimes.
Thank you, Doug. Anybody else? Any updates on the preparative columns side?
Steve Luke from Thermo. Again, along a similar line to Doug, the Hypersol Gold range of columns available from 1.9 micron all the way up to 12 micron in all chemistries. So again, scalability and availability in prep format. Interestingly enough, we get a number of inquiries for prep formats of solid core columns, and I wonder if people aren't quite getting the point of solid core when they're looking at prep formats for them.
I see. Okay. All right. Bill or Wayne, anything to add? If not, just to wrap up, I would like to ask each of you just to comment on, what users can see in terms of column chemistry, column technology over the next year or so. If you can sort of give us some futuristic perspective on where the field is headed.
This is Bill Long at Agilent. This year, as Mike Talk indicated, we're working to basically copy all of our totally porous phases on for superficially porous columns. This actually will allow, and I guess in a way I should have answered something on the prep. While we don't really think that the prep use of solid core or fused core or superficially core material is for prep, we find it that by having the same phases and an established way of transferring methods from one type of particle to another, that we will actually help meet the needs of most separation scientists. But right now, our main goal at this time is to basically match out all of our Zorbax phases onto our porous shell lines, much as we've done with the 1.8 micron materials.
Okay, thank you, Bill. Doug, do you want to go next?
Sure. Let's say for the short term, I think the things you're going to see will be much more application specific column chemistries, things designed for a particular challenging market or application, things like a glycan or peptides or proteins. And then from waters, the thing that we're focusing on is sort of a little bit outside of the subject matter for today. In this sort of reversed phase centric type presentation, which was basically looking at UPC squared, which is sort of modernizing supercritical fluid chromatography, and to do some things that maybe aren't quite so easy with or undesirable with normal phase chromatography or GC.
Thank you. Thanks for the feedback. Steve?
What I think users will see happening in the upcoming year is more and more selectivities added to the pantheon of solid core materials, including some special selectivity materials, possibly something application specific, but certainly some different selectivities to counter the perception that there sometimes is that there's too narrow a range of selectivities available in solid core. I think we might also start to see people playing around with the design of solid core particles in terms of diameter, or in terms of ratio of core to porous shell thickness.
Mm-hmm. Right. Thank you. And finally, Wayne?
Yeah, I would. Well, one thing on this, I didn't comment on the prep side, but one interesting note on the, let's say, the smallest size of prep, 10 millimeter ID range, the Asenis Express fuse core is offered in that size. So if you are doing, let's say milligram level, and you are working with a fuse core and you just want to transfer straight to a 10 millimeter ID column, that is available. But I think as far as trends, I'd echo what most have already said. I think application-specific columns, you'll see more of that. I think certainly fuse core and fuse core type columns, you'll see an expansion in terms of phases and particle architectures, and certainly the learnings from all the fuse core types of architectures will also further develop porous particles, I believe.
Okay. All right, well, this brings us to the end of our webinar. The contact information for our speakers is shown on your screen, and you're more than welcome to contact them and get their advice and help on how to improve the performance of your columns. On behalf of Lab Manager, I would like to thank all our sponsors, Agilent Technologies, Waters, Thermo Fisher Scientific, and Sigma Aldrich, Supelco, for their participation and support. And of course, my sincere thanks to all the speakers. They have really put in the effort to make their presentations very informative and relevant to the users. So thank you all. This webinar, as I mentioned earlier, will be archived on Lab Manager's website for 6 months. And you can also view past webinars that we have done on topics such as LCMS, GCMS, UHPLC, and we had done a webinar on HPLC columns and GC columns as well. So that's all on the website, so when you have time, do take a look at it. Thank you all once again for your time and attention. Our webinar next week will focus on the use of mass spectrometry for food safety analysis. So hope you can join us then. Goodbye.